Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 6.4, their normal approximation to the binomial distribution. Our objectives for today are to use the normal curve to approximate binomial probabilities. A binomial random variable represents the number of successes in a series of independent trials. The sample proportion is found by dividing the number of successes by the number of trials. Since the sample proportion is approximately normally distributed whenever n times p is greater than 10 and n times 1 minus p is greater than 10, the number of successes is also approximately normally distributed under these conditions. Therefore, the normal curve can be used to compute approximate probabilities for the binomial distribution. Recall that if x is a binomial random variable with n trials and success probability p, then the mean of x is n times p, the variance of x is n times p times 1 minus p, and the standard deviation of x is the square root of n times p times 1 minus p. Binomial probabilities can be computed exactly using the techniques described earlier. If the number of trials is large, using these methods by hand can be extremely difficult because many terms have to be calculated and added together. If the following conditions are met, binomial probabilities can be approximated using the normal distribution. Let x be a binomial random variable with n trials and success probability p. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then x is approximately normal with mean n times p and standard deviation the square root of n times p times 1 minus p. The binomial distribution is a discrete distribution, whereas the normal distribution is a continuous distribution. The continuity correction is an adjustment made when approximating a discrete distribution with a continuous one, which can improve the accuracy of the approximation. Suppose a fair coin is tossed 100 times. Let x represent the number of heads that result. Then x has a binomial distribution with n 100 and success probability p of 0.5. If we want to compute the probability that x is between 45 and 55, the probability will differ depending on whether the endpoints 45 or 55 are included. To compute the probability that 45 is less than x is less than 55, the areas of the rectangles corresponding to 45 and 55 should be excluded. To approximate this probability with the normal curve, compute the area under the curve between 45.5 and 54.5. If you look down here, we can see that this now does not include 45 and 55. To compute the probability that 45 is less than or equal to x, which is less than or equal to 55, the areas of the rectangles corresponding to 45 and 55 should be included. To approximate this probability with the normal curve, compute the area under the curve between 44.5 and 55.5. So if we look down here, we can see now 45 and 55 are included. Those rectangles that contain them are included. Example 1. Let x be the number of heads that appear when a fair coin is tossed 100 times. Use the normal curve to find the probability that 45 is less than or equal to x, which is less than or equal to 55. Number of trials is n, which equals 100. Since the coin is fair, the success probability is p equaling 0.5. Therefore, n times p is equal to 100 times 0.5, which is equal to 50, which is greater than or equal to 10. And n times 1 minus p is equal to 100 times 1 minus 0.5, which is equal to 50, which is greater than or equal to 10. We may use the normal approximation since both are satisfied. We compute the mean and standard deviation of x. So mu is equal to n times p, which is equal to 50 from above. The standard deviation is equal to the square root of n times p times 1 minus p, which is equal to the square root of 100 times 0.5 times 0.5, which is equal to 5. Because the probability is the probability 45 is less than or equal to x, which is less than or equal to 55, we want to include both 45 and 55. Therefore, we set the left endpoint to 44.5 and the right endpoint to 55.5. We can use tables or technology to find that this probability is, so the probability that 45 is less than or equal to x, which is less than or equal to 55, is approximately 0.7287. Example 2. A fair coin is tossed 100 times. Let x be the number of heads that appear. All right, and we're going to do three things. To approximate the probability that x is less than or equal to 55, we would want to find the area to the left of 55.5. To approximate the probability that x is greater than or equal to 55, we would want to find the area to the right of 54.5. And to approximate that x is equal to 55, and to do that, we would want to find the area between 54.5 and 55.5. So the first one is here in this upper left-hand corner. So this is the probability that x is less than or equal to 55. So you can see all the rectangles. And then we want to go to 55.5 and go less than that. So we shade everything to the left of that, and that's the area we're trying to find. The probability that x is greater than 55, so we want 55.5. So we go again to 55.5, and we shade everything to the right of it. To approximate that x was exactly equal to 55, you can see the shaded area right at 55, and then everything to the left and to the right we're not worried about. So we're trying to get from 54.5 to 55.5. It can be difficult to know what to do with these continuity corrections, so this is kind of like a cheat sheet. So when the probability of A is less than or equal to X, which is less than or equal to B, we're going to go from the left of A and to the right of B. So we're going to take A and subtract 0.5 from it, and B, we're going to add 0.5, and that'll include A and B. If we want just less than B, we're going to add 0.5 to B and go to the left of that. If we want greater than A, we're going to take A and subtract 0.5 and then everything to the right of that. If we want exactly a certain A, we're going to subtract 0.5 from it and add 0.5 to it and find the area between those two numbers. Example 3. The Statistical Abstract of the United States reported that 66% of students who graduated from high school enrolled in college. 100 high school graduates are sampled. Let x be the number who enrolled in college. Find the probability that x is less than or equal to 75. So first we have to do our checks. So first check is n times p. So we have 100 times 0.66, which gives us 66, which is greater than or equal to 10. So that's good. Now we have to check n times 1 minus p. So again, 100 times 1 minus 0.66, which gives us 34, which is still greater than or equal to 10. So that checks out. So now we can use this normal approximation. So first we have to compute the mean, which was n times p, which we already figured out is 66. The standard deviation is the square root of n times p times 1 minus p, which is equal to the square root of 100 times 0.66 times 0.34, that's 1 minus p, which is equal to 4.73709. Because the probability x is less than or equal to 75, we compute the area to the left of 75.5. Using tables or technology, we find that this probability is 0.9775. So what this is saying is there's a 97.75% chance that there were 75 or less students that enrolled in college out of the 100.